Hello, welcome to another module in this massive open online course. Alright, so we are looking at time division multiplexing. Alright, so let us look at other aspects of time division multiplexing in this module. Okay, so we are looking at time division multiplexing, that is TDM technology to multiplex several signals over a single channel for transmission. Okay, so this is your time division multiplexing technology. Now let us start by looking the bandwidth required for TDM. So what we want to look at is, first we want to answer the question, what is the bandwidth, required for TDM. Now if you look at this, for instance, let us say let there be n signals. So let us say we are multiplexing n signals using time division multiplexing. So let n signals be multiplexed and they are sampled with, all are sampled with sample at equal intervals Ts. So sampling interval for each signal equals Ts. Okay, so there are n signals and the sampling interval for each signal is Ts. Now if T is the spacing between the samples, if T equal to the denotes the spacing between samples of your TDM signal, that is if we look at your TDM signal, correct, and let us say we look at the samples of the multiplexed signal. So this is sample of signal 1, sample of signal 2, sample of, so this is sample of signal, this is samples of the multiplex signal. So sample of signal 1, sample of signal 2, this is sample of signal 3, sample of signal 3, so on and so forth. And if this duration, the duration between samples is T. Now we have to note that the sampling duration of each signal is uniform, that is Ts, which means every signal has a single sample in Ts. Therefore, n signals will have n samples in the interval Ts, right. So each signal contributes one sample in Ts, implies when you look at n signals, so naturally they are going to give n samples. Therefore, distance between, therefore the spacing between samples, since in Ts there are n samples, spacing between samples of your TDM signal equals Ts divided by n, that is equal to T. So, sample spacing equals spacing between samples equals of TDM signal equals T, and we have T equal to Ts divided by n. Now, bandwidth that is required for transmission of TDM signal TDM signal, this is equal to, well, the bandwidth is 1 over 2T, which is equal to, well, we have seen T equals Ts divided by n. So, this is 1 over 2 Ts divided by n, which is n over Ts. Now, this is n over twice Ts, which is half n Fs, where Fs equals the sampling frequency, Fs equals 1 over Ts equals the sampling frequency. Okay, so, Fs equals 1 over Ts, which is equal to the sampling frequency. Now, if we sample at the Nyquist rate, then if we sample the signals at the Nyquist, the signals have to be sampled at Nyquist rate, right. By the Nyquist criterion, the sampling rate, the sampling frequency Fs has to be greater than at least 2 Fm, where Fm is the maximum frequency of each signal. Okay. So, by Nyquist criterion or from the Nyquist criterion, we need Fs greater than or equal to 2 Fm, which means bandwidth. Therefore, if we call this bandwidth required for transmission as f of TDM, we need f of TDM equals, well, half n into Fs, but Fs greater than or equal to 2 Fm. Therefore, this is greater than half n into twice Fm, which is equal to n times Fm. Therefore, we need the bandwidth of the time division multiplexed signal to be greater than or equal to n times Fm, where Fm is the, well, so Fm, so this is n, this is equal to number of signals multiplexed, and Fm is the maximum frequency of the multiplex signals. This is equal to maximum frequency component of each signal. Okay, maximum frequency component of each signal. Okay. So, basically the bandwidth of, you can say bandwidth of TDM signal is greater than or equal to number of signals multiplexed the product of number of signals multiplexed into maximum frequency, that is, or you can say bandwidth of each signal times times the bandwidth of each signal. So, that is the relation that we have for the bandwidth of a TDM signal. So, the TDM signal, of course, naturally since it is multiplexing a large number of signals, we require a large bandwidth, right. This bandwidth is related to the sampling frequency, which is in turn related to the bandwidth from the Nyquist criterion related to the bandwidth of each signal. So, what we have shown is the bandwidth FTDM of this time division multiplex signal has to be at least n times the bandwidth of the signals being multiplexed. Okay. So, it requires a large bandwidth for transmission. Okay. Now, let us do a simple look at a simple case study to understand the construction and working of a typical TDM signal, that is a typical TDM system, that is a time division multiplex system, also known as a T1 system. Okay. So, now what we want to do is we want to do a case study for TDM system. In particular, we want to consider one particular TDM system, that is the T1 system that is used for telephony. This is used for voice communication, voice telephony. Okay. So, this is used for telephony. Okay. Now, the TDM system, this comprises of 24. Now, the T1 system comprises of 24 voice channels over separate pairs of wires over separate pairs of wires with regenerative repeaters, because the signal dies down with distance, separate pairs of wires which basically amplify with regenerative repeaters at approximately 2 kilometer intervals. Okay, and why do we need these regenerative repeaters? We need the regenerative repeaters to repeat the signal because signal strength decreases with distance. Because the signal strength decreases with distance. Okay. So, these regenerative repeaters, what they do is they amplify the signal, regenerate, that is prevent the signal from dying down. See, they amplify the signal, amplify the TDM signal. Okay. So, this regenerative repeaters amplify the TDM signal. And this is used for voice, T1 used for voice communication. And voice signals have a frequency range that is 300 hertz to, so the voice signal frequency band is 300 hertz to 3.1 kilohertz. Okay. So, what you have is basically you have a voice spectrum that looks something like, you have a voice spectrum that looks something like this. So, it starts at your 300 hertz and it, so something like starts at 300 hertz and goes up to 3.1 kilohertz, that is 3100 hertz. Similarly, if you can look at this, it starts with this and goes up to, well, right. So, this is your voice spectrum. This typically starts at your minus okay. So, this is your voice spectrum. So, it starts minus 300 or minus 3.1 kilohertz to minus 300 hertz. This is your how your typical voice spectrum looks like, or voice signal. This is the spectrum of the voice signal. Okay. Now, therefore, you can see the maximum frequency FM, that is your maximum frequency in this case study of the voice signal. We are consider the multiplexing of 24 voice signal. Maximum frequency equals, well, that is 3.1 kilohertz. That is the human frequency, maximum frequency of human voice signal is 3.1 kilohertz. Okay. Now, therefore, the sampling frequency Fs from Nyquist criterion. So, from Nyquist criterion, to avoid distortion, we need Fs greater than or equal to twice Fm, which is twice into 3.1 kilohertz, that is equal to 6.2 kilohertz. Okay. So, we need 6.2 kilohertz. However, Fs greater than or equal to, so we need minimum Fs is basically 6.2 kilohertz. That is to avoid aliasing. We know this, right? This is basically the Nyquist sampling rate, minimum required sampling rate. This is the Nyquist sampling rate to avoid aliasing. Okay. Now, this is quantized with a mu log quantizer. However, it is typical. So, even though 6.2 kilohertz is sufficient, it is typically sampled at 8 kilohertz. At Fs equal to 8 kilohertz, that is 8 kilo samples per second. Okay, 8 kilohertz sampled at 8 kilohertz means 8 or 8000, 8 kilo means 8,000 samples per second. So, even though the minimum required sampling rate is 6.2 kilohertz, it is oversampled, right? It is sampled at a slightly higher rate, it is sampled at 8 kilohertz, that is 8 kilo samples or 8,000 samples per second. Now, each sample is quantized using 8 bits, alright. So, we have, well, what do we have? We have each sample is quantized by a mu log quantizer using 8 bits, okay, with 8 bits. Mu log quantizer with 256 levels. Well, 256 equals 2 to the power of 8 implies 8 bits per sample. This implies 8 bits per sample. Therefore, we have 24 voice signals, right, 8 kilohertz sampling rate. So, net system we have is 8 bit per sample from each of n equal to 24 n equal to 24 voice signals, that is your T1 system. So, what you have in your T1 system is basically, if you look at this, you have, well, you have signal 1, signal 2 is 24. So, you have V1, V2, so on up to V24. All these are multiplexed over a single channel. So, all these are TDM, time division multiplexed over a single channel. Okay. So, naturally what is the, well, sampling rate equal to 8 kilohertz, implies sampling duration equals, well, 1 over 8 kilohertz, Ts equal to 1 over 8 kilohertz, that is equal to 125 microseconds. Okay. Now, this we can also call this as frame duration, we can also call this as frame duration. Okay. In this, basically each signal generates, so in this each signal generates one sample, each of the 24 signals generates one sample. In a frame duration, each of 24 signals generates one sample. Each sample is quantized using 24 bits. So, in a frame duration you have, that is, number of samples in frame, or you can say number of bits in frame equals, well, 24 number of signals into, well, 1 sample per signal into 8 bits per sample. So, 8 bits from the 24. So, 24 signals, each generates a sample with 8 bits. So, 24 into 8 plus 1 synchronization pulse or synchronization bit. So, that is equal to 24 into 8. So, 192 plus 1 synchronization, 1 sync bit, that is equal to 193 bits. Total bits per frame equals 193. So, in this TDM T1 system, you can see in the TDM system, in the case study that we are doing, number of bits per frame equal to 193, which implies, well, duration of each bit or time interval between bits, frame duration is 125 microseconds. Time duration between bits equals 125 microseconds. Okay. A time duration between bits is 125 microseconds divided by, well, 193 bits. 193 bits, that is equal to, well, 0.647 microseconds. And bit rate of the T1 system bit rate of T1 system is basically 193 bits divided by 125 microseconds, that is equal to, well, 1.544 megabits per second. So, this is basically the bit rate of the T1 system. If we calculate that, that is a huge bit rate, that is equal to, well, 1.544 megabits, that is into 10 to the power of 6 bits per second. That is your bit rate of the T1 system. Okay, and the T1 system is a classic example of a time division multiplex system. This is a classic example of a TDM system, and therefore, what we have is what we have seen in this module is we have seen some important aspects of the TDM system, that is what are the bandwidth requirements of a TDM system. Also, we have done a case study of a classic example of a TDM system, that is a T1 system which combines 24 digital voice channels into a single system, right, and we have seen that this has a huge bit rate of 1.544 approximately 1.544 megabits per second. All right. So, we will stop this module here. Thank you.